Hello everyone, my name is Juan Lopez and today I will discuss the paper Mitigation of Sensor Attacks on Legacy Industrial Control Systems. The authors of this paper are Luis Convita, Álvaro Cárdenas, Nicanor Quijano. This paper was presented in the 2017 IEEE Third Colombian Conference on Automatic Control. To give you a quick description of the presentation, I will first give you a background on industrial control systems and their vulnerabilities. I will then move on to the potential integrity attacks of these industrial control systems and how to mitigate them. I will give a review of potential processes that can be used to mitigate these attacks and explain why they might not be the best solution when working with legacy control systems. I will then describe the use of Leuenberger observers in order to detect and isolate attacks before reconfiguring the control system. Industrial control systems today have different types of devices that allow them to work. These devices and systems include SCADA, which is Supervisory Control and Data Acquisition, PLC, Programmable Logic Controllers, and DCS, Distributed Control Systems. From a security perspective, the industrial control system's main priority is availability, followed by confidentiality and integrity. Industrial control systems include legacy systems as well. These legacy systems have to work along with more modern components that are added to the industrial control system for different reasons, such as improving goods, increasing efficiency, or creating new products. Specifically, in this paper, the authors focus on improving the integrity aspect and assuring that no sensitive data can be modified by unauthorized users. This will be avoided by not allowing the attacker to reach the sensors or actuators information and modify it. In a similar manner, the controller has to be protected, since if it is modified, the behavior of the entire system will change and won't be the same as the original system's set output. In this graphic, as we can see, we have the controller, followed by the actuator and the process. We also, in the process, we have some disturbance inputs. And connected to the outputs, we have some measurements. These measurements are sensors that send information to the controller. The controller processes this information, and depending on the control law, it will modify the system to get the desired output. Vulnerabilities of industrial control systems. Many industrial control systems have numerous vulnerabilities due to a lack of patching. Since creating patches often requires stopping the control system completely, which can be costly. They are not done also frequently. Replacing legacy industrial control system completely is very difficult and expensive as well. Requires extensive planning and also requires a stop in production sometimes. However, the addition of new devices also adds vulnerabilities to the industrial control system. For instance, a wireless communication device that allows the system to control and communicate other devices across a warehouse will allow the attacker and will pose a threat to the system, since it can create a backdoor to the control system. For this reason, it is necessary to create a system that mitigates the effect of attacks on control systems. On this chart, we can see how facing integrity attacks on sensor of legacy industrial control systems and their methods. We have the default detection, and then we also have isolation and reconfiguration. From fault detection and isolation, we have the FDI. From the FDI, we have the base model method and the database method. From the model-based methods, we have the qualitative and quantitative. And the quantitative, we have state estimations that is divided in observer-based method, deterministic systems, and Kalman filter-based method, stochastic systems. Related processes. The paper discusses some different processes used to isolate and mitigate industrial control systems vulnerability and attacks, and discusses why these systems are not ideal for legacy control systems. Irrigation channel system is based on a bank of observers and work for detection and isolation in the system. However, they do not work for reconfiguration. Also, SCADA is for the prevention of reply attacks and is based on noisy control authentication signal. Like irrigation channel system, it also works with the fault detection integrity of integrity attacks. The stochastic system uses random variables to discover a pattern that can be analyzed mathematically to discover a change in the system. The authors also mention an stochastic technique where they inject a random signal in the actuator, which is unknown to a sensor, and this technique makes sure that malicious sensor is detected or it is denied from adding distortion to the system. Stochastic control has some downsides, and is that it's not always compatible with legacy systems, and also might have a significant computational load. All the related processes or work discussed by the author can detect and isolate integrity attacks, but have not been developed to be used with control reconfiguration. Showing the image from earlier, I have highlighted the method explained in the paper as the best way to mitigate the attack of legacy control systems. We will now discuss the author's idea for determining on attack using observer-based methods, which are the best used on deterministic systems. Mitigation of attacks. As we can see in the image, we have first detection of the attack, followed by isolation, and then finally control reconfiguration. The mitigation of the control system is based on the modification of the control action. The idea is so that the control action can correct itself, so this modification won't affect the output of the system. The paper states they use a fault tolerance control model to prevent the system from a failure. If the fault tolerance control doesn't successfully correct the system, the attack can damage the system in a way that might be dangerous from the people around the system and also their access. The fault tolerance control works by detecting the attack, then isolating it, and then redesigning the control system in order to prevent a total failure. The attacker will try to tamper the sensor by injecting a signal. Therefore, the system should be able to correct the incorrect control action, and this is called control reconfiguration. Attacks against system sensors. This method requires an observer design based on a dynamical model of the physical system. For the purpose of this paper, we're going to use a plant, we're going to have a controller, we're going to have attack on sensors, we could also have attack on actuators, but on this paper we're gonna base just on attack on sensors. Attack detection, attack isolation, and control reconfiguration. Plant, controller, and attack on sensors. For the plant, we use a deterministic discrete time, linear time invariant model. The model must be accurate in model-based systems. For the controller, we assume the system is a closed loop. And for the attack, we're going to have a signal that is going to be injected on the sensor. On the graphic on the right, we can see how the system is a closed loop. The controller will connect to the actuator with the physical system, from the physical system to the sensor, and the sensor will come back to the controller. In the center of the chart, we have the human-machine interface. This interface connects a person to a machine, system, or devices. Plant model. For this plant model, we use fault tolerance control model to mitigate the sensor attack. In this slide, I will explain the simulation that the authors used to describe how their fault tolerance control can be used to prevent attacks on sensors. This is based on 3 tanks, and the objective is the control system to maintain the liquid level of 2 tanks in relation to a set point that has been previously determined. The system has 2 valves that regulate the liquid that enters the tanks 1 and 2. In the attack, we assume that the system is a closed loop and uses 2 variables, L1 and L2. The tanks will reach the desired liquid level each time that the level varies from the set point by manipulating the variable values. Each time that the tank reaches the L1 variable value, there will be a small change in L2 variable. Similarly, it is a value that reaches a variable L2, there will be a small change in L1. The objective of this attack is overflow the tanks. This will be attained by having an abrupt change in tank 1, but a small change in the tank 2. The variables change as a result of the attack. Therefore, the controller changes its state and the signal of output also changes. In the right image, you can see how the attack on sensor 1 is easier to detect than the attack on sensor 2, since the change is more aggressive. On the graphic on the left, we can see how the sensor will behave in a normal state. Attack detection. The attack detection in this paper is developed by using Leuberger observers. Leuberger observers are estimators that are connected to the system that produce estimates of the variables since they are driven by the system itself. We have 2 different Leuberger observers. We have full order observers and reduced order observers. The full order observers have the same dimension as the original system. On the other hand, reduced order observers uses system measurements to estimate the variable that can't be directly taken from the system. With Leuberger observers, when there is a signal injection in the errors, it is designed in a way where it detects an anomaly and the signal error between the initial estimated error and the signal injected on the sensor will not equal 0. As we can see in the formula, when the number is not 0, we will know that we're in the presence of an attack. One of the downsides of the observers is that there may be other disturbances on the sensors that are no attacks, so it could give false positive information. This type of false positives continue to be created due to a lack of a memory that could store past false positive and then detect a pattern. To avoid this, we could set a threshold a little higher so we can avoid this false positive. But the downside of this is that true attacks might go on undetected. Using this method also does not help determine which device is creating the problematic data. Attack isolation. Used to determine which devices are sending misleading data. Also structure the residuals contained via servers that are sensitive to a specific signal are developed using unknown input observers. Designing an unknown input observer for each output allows for anomaly isolation to identify where information is modified. Once an attack is detected using the Lurberger observers, an attack isolation is necessary to determine where the manipulated data is coming from. Unknown inputs observers, or UIOs, are developed to isolate the anomalies and find the altered information. Unknown input observers work by creating full order observers that are triggered by specific signals. It is important to mention that unknown input observers are required for each output in order to detect an anomaly on a sensor. Therefore, we need to create a bank of observers. In this paper, the author assumed that there is only one active attack and there are no simultaneous anomalies on the sensor. Boolean logic is used to collect the outputs from each sensor. If there is an attack on the system, the output will be true. Otherwise, the output will be false. Control reconfiguration. Recomputation of the new control actions. Also, we need to track the error of state variables. We know that when the error not equals 0, we're in the presence of an attack. Also, the control law should readjust the sensor output by canceling the disruptions in the input. Control reconfiguration objective is to compute a new control action on the variables if an attack is detected. For instance, if an attack error injects a signal on a sensor, the value of the tracking error will not be equal to 0, and then control law will try to bring the error back to 0. The same case will apply in the scenario that is a sensor fault. The control law will need to prevent the sensor from responding. Attack mitigation. We have attack isolation and recompute and add results to the control action. After the attack is detected and isolated, the new control will compute and add a control action and add it to the sensor information. Like you can see in the graphic, the control reconfiguration is capable of responding to sensor attacks, and you can also see what the graphic would look like if the attack hadn't been mitigated. So on the graphic up top, you can see the sensor 1 and how the blue line shown how the control reconfiguration actually take action and correct the incorrect signal. As well on the sensor level 2, you will see how the signal was corrected on blue. On the conclusion, we have that conventional tools from fault detection, isolation, and reconfiguration can be used to face integrity attacks on sensor of legacy industrial control systems. Also, we study the output will not be affected if the system law is able to correct itself. This type of model can be also escalated, which means it can be applied to larger systems or bigger systems. Attacks on actuators can be addressed using this technique in the future, but for the purpose of this paper, we only focus on sensors attack. Thank you for listening.